This conference will now be recorded.
All right, so welcome everyone. This is the 71st OCP session, and today we have Lu Pan from Meta, which Lu Pan is a software engineer and has been with Meta for the last 7 years. Spent most of his time working on large-scale distributed systems, primarily focusing on consistency, reliability, and scalability. And today's talk will be basically comparing fbclock with the hybrid logical clocks, and probably we'll have some insight on TrueTime and all of these things. So Lou, let's see if I can make you a presenter, and usually that goes smooth. Not really. We'll see. Hopefully it goes smooth this time. See if you can share your slides. And while you're getting ready, Lasse, anything you want to add?
No, my God, no. 71. It's good. Making progress.
Awesome. That went smooth. Okay, so with no further ado, Lou, the floor is yours.
All right, thank you, folks. Can you guys hear me just fine?
Yes.
All right, cool. So I'll start here. Hey guys, my name is Lou from Meta, and I've been at Meta for over 7 years since worked on large distributed systems like Tau, and which you might have heard of, which powers the social graph at Facebook and Instagram, WhatsApp, Oculus, and so on and so forth. Today I want to mostly talk about comparing PTP-based FB clock versus hyperlogical clock from a application, specifically from distributed databases applications perspective, and then the pros and cons between the two, and then at a high level might help us decide which one we should use. So to start with, like if there is a single keyword in concurrency control and or distributed system, is probably ordering, and then timestamp is a very natural way to construct the ordering, and hence commonly used in either single host for MVCC or in distributed systems for ordering events. So, but when it comes to the choice of timestamps or clocks, there are many different combinations that you can choose from. From the underlying sync protocols, you have PTP, NTP, and so on and so forth. But the actual clocks built on top of it, you also have FB clock or TrueTime. You have hyperlogical clock. You have just physical clock like time 2. You also have other forms of logical clock, vector clocks, or whatnot. Which one we should use, and what are the pros and cons between these options? So today I mainly will compare some of these clock choices from a distributed database applications perspective. I will not cover pure logical clocks, for example, logical clock or vector clocks, because hyperlogical clock affords like a superset of logical clock features anyway. Well, and also doesn't have the prohibitive space cost associated with vector clocks. So this is the agenda. Like I'll briefly talk about PTP-based FB clock, and I assume the audience is mostly familiar with it. And then I'll briefly talk about commit weight and the linearizability, and spend some time talking about what is HLC, and spend most of the time comparing between them. Like for example, PTP-based HLC versus NTP-based ones, and then FB clock versus hyperlogical clock. So for a brief introduction, so PTP stands for Precise Time Protocol. It's a hardware-based clock synchronization protocol. And FB clock is the user-facing library for accessing PTP. So it presents this window of uncertainty. So it knows the earliest and then the latest timestamp instead of just a single one. And then the API was first introduced by Spanner in 2012 under the name TrueTime. So it's the same API. And so what is commit weight? So I bet a lot of people have heard about it, especially for people who work on clocks and TrueTime API or PTP. So to say, so I'm going to spend some time on this because it is important when it comes to the ordering construction. So say we want to have the following property. I took the screenshot from the Spanner paper. So I want to have this property that I want to have transaction 1's if transaction 1's absolute commit timestamp is less than transaction 2's absolute start time, so which means like in terms of absolute time, transaction 1, E1 in this case, is committed before the transaction 2 is started in terms of absolute time, then I want transaction 1's commit time, in this case S1, to be less than transaction 2's commit time, in this case S2. So that's the property we want. And there's like naturally the reason why we want it is because if this doesn't hold, then that means the commit timestamp ordering minted by Spanner, for example, is going to be inconsistent with an external observer. So this is a nice property to have. So how do we ensure this property? And then if it is happening on a single database host, then it can be ordered locally. You can hold logs. You can, usually this property holds if you're talking to a single database host. But when it comes to a geo-distributed database with many shards and whatnot, in terms of Spanner, different Paxos groups, which is analogous to shards in many cases, then like how do we order those events? Like transaction 1 might be happening on shard 1, and then transaction 2 might be talking to a completely different shard. Like how can we ensure that they are ordered properly and satisfy this property? So here's a naive solution before we talk about commit weight, is that we can sort of use coordination. So when client A is trying to write transaction 1, in this case E1 to shard 1, it can try to get a commit timestamp by talking to the other shard. And then by reserving a transaction commit timestamp from the other shard 2, then after receiving the reply, then we say, okay, I'm going to mint the transaction timestamp on the shard 1 after the coordination. Then in this case, this property obviously holds, because if transaction 2, E2 only starts after the transaction 1 is committed, then the second shard's local transaction timestamp must have already passed the E1 S1, so that S2 is always going to be higher than S1. The problem with this, though, by the way, a lot of people this is kind of people familiar with two-phase commit. This is one way of doing two-phase commit for transaction commit, or two-phase locking for concurrency control, but essentially through coordination. And then one obvious problem with this is it doesn't scale very well. Let's say if you only have 2 shards, yeah, sure. But what if you have 10 million shards? Now what are you going to do, right? Like, so if we write to 1 shard, if you coordinate with the rest of 10 million shards, then this obviously doesn't work very well. So introducing commit weight, and then so remember, this is the property we want to construct and we want to satisfy, and how can we satisfy this property using commit weight? Here's again a screenshot from the Spanner paper, and then so we're going to talk about how Spanner does this. So once you have a commit timestamp picked, for example S1, so this is the first row, the S1 less than absolute timestamp of E1's commit timestamp. We do not commit. So let's say we pick the transaction commit timestamp S1 already. We'll talk about how we pick it in a few seconds. Let's say we picked it, and then but we do not commit until, or we commit but we do not return a commit until S1 is definitely in the past. So how do we know S1 is definitely in the past? Well, this is where the window of uncertainty comes handy. So we pick the transaction timestamp and we wait until the T earliest or the oldest timestamp to pass the S1. Then we know that the commit timestamp is definitely in the past. No one is going to get a timestamp earlier than this, anyone. Then we can we can actually commit the transaction and return to the client. So this is called commit weight. And then if you look at the second row, so by doing commit weight, we satisfy the first condition here, S1 less than the absolute timestamp of E1's commit timestamp. But let's look at the second one. It talks about E1's commit timestamp less than E2 start. This is the assumption, because this is the assumption of the property we want to satisfy. The third one is E2's start timestamp is less than or equal to E2's server timestamp. This is trivially satisfied by causality, because someone has to start a transaction first before the server was able to receive it. So because the communication implies causality, hence like the absolute time inequality here holds. The fourth rule, which I want to call out to it, a lot of people omit this, is that that's why we actually wait out 2 rounds of uncertainties when people say to commit wait, is that there's another way here called start wait, is when the server receives this transaction, in this case, the spanner, receives this transaction request, it doesn't, you have to pick a transaction timestamp S2, which is definitely in the future. So to satisfy this ordering. So when the spanner server receives a transaction request, and then you have this, then on the spanner local server, you call TrueTime or PTP fbclock, then you get a window of uncertainty. And you have to pick a commit timestamp that's after the now.latest. So that's definitely in the future. And then by doing so, then through transitivity, we can, through all this line set of inequations, you can see that S1 is less than S2, which is the property we want. So you'll pick the commit timestamp to be definitely in the future, and then you wait it until it's definitely in the past. So you wait basically 2x of the window of uncertainty. So Spanner famously leverages this TrueTime and a commit wait to achieve external consistency, aka linearizability. And then, so by definition, linearizability's definition is like, loosely speaking, is for a system to be linearizable. That means every single operation appears to take place atomically in some order and consistent with the real-time order of those operations. And there's a common misconception of saying like linearizability is about capturing causality everywhere, like not just read your right, but read everyone's right or read all right. It's just like any type of causality that can be captured in the system is captured, then hence it's linearizable, which is not true actually. So if you look at this example, so assuming that you have 2 concurrent writes, W1 and W2 to the database, while W1 and W2 are in flight, then let's say we also have 2 concurrent read operations, R1 and R2. If R1 observes W1 but not W2, and R2 observes the opposite, like observes W2 but not W1, then this is not linearizable by definition, because R1 implies that W1 happens before W2, but R2 implies the opposite. And then so this is a violation of linearizability. But you can see there's no causality being violated here, because all those operations are in flight. There's no implied causality between any pairs of these 4 operations, but this is still a violation of linearizability regardless. So, but how does Spanner solve this problem, right? Like, so it's not just about capturing causalities that like ordering those write transactions. So Spanner's solution naively is just saying like we want to order reads as well using timestamps, and then it's the same timestamp, which is also using TrueTime. So everything is globally totally ordered using those timestamps, and hence by definition linearizable. So concretely, so how they do it is by for a single shard read, then they just read the Paxos group leader, which is essentially doing a critical read, and then hence satisfying linearizability. But if you are doing a multi-shard like linearizable snapshot reads, then they will actually use the timestamp, saying like the client will pick the latest timestamp and then request a snapshot at that timestamp across multiple shards. And then because again the read is also ordered using those using the timestamps, so it satisfies the linearizability. And also because we pick the latest, so it's not going to violate any causality. All right, so let's talk about hybrid logical clock. So, so hybrid logical clock is proposed in 2014, which is actually 2 years after the Spanner paper. And then the main kind of selling point of the paper is that is to be an alternative to TrueTime and the logical clocks, so that it's capable of providing consistent snapshots without special hardware or commit wait. So that looks very appealing, right? And so here's a naive HLC implementation, which we're going to use as an example. There's a slightly a 2-tuple form of HLC, which we're going to omit just for simplicity. So so here, the naive HLC, how do you compute the HLC is very straightforward, is that you pick the next HLC to be the maximum of any, like the highest previously observed timestamp plus one, and then the current physical timestamp. And how you get the physical timestamp, you can get it from PTP or NTP or whatnot. But that's how you compute the next HLC. And then you can see that it blends in like both the logical aspect of it, as well as the physical timestamp aspect. So that's why it's called hybrid logical clock. So and then by doing so, you can capture causality. And then in the paper, like the HLC was built on top of NTP, piggyback on every single kind of clock synchronization message. But it's also explicitly called out that it doesn't have to be like that. Like they can piggyback on any kind of ad hoc synchronization protocol. What this means is that we don't need to carry kind of HLC synchronization messages on all network communications to get the benefit. Like you only need to propagate it to capture the causality that you care about. And then, assuming you capture the causalities, then the HLC will reflect it because it will never be the same. The one on the receiving end is always going to be higher. The event happened, then the HLC will also raise forward. So by doing so, if the event E happens before event F, and it's a happen before relationship that's captured, then the HLC event E's HLC will be less than F's HLC by definition, because that's how it's defined. So that means if you take a cross process or distributed snapshot by just picking one HLC, like let's say HLC 10 across different shards of database, and then they must be concurrent. They cannot have like a causality violations. And then that's how they claim that is to be a consistent snapshot, which is true. But also there are some caveats which we'll get to in a second. That's why I put an asterisk next to consistent snapshots here. Before we talk about HLC versus fbclock, I just want to get one thing out of the way, which is PTP-based HLC versus NTP-based HLC. So they're both HLCs, but they're just based on top of different clock sync protocols and then the underlying kind of physical clock. So are there any differences, and then are there kind of pros and cons between them? So first we want to introduce this concept called HLC stragglers and HLC rushers. So here the P0 is essentially an HLC stragglers because due to maybe slowed event generation or whatnot, so its HLC is lagging behind. And then here P2 is essentially a HLC rushers because mostly likely like fast event generations. So it bumped its HLC, for example, far too ahead of physical time. Let's say physical time is around 7, but it's at 20. So this is this can happen even though in the paper I also talked about like you can always try to bump this and then using your notion of current now based on physical time, but it's always subject to clock skew. So you can imagine all this kind of a rush ahead or straggling behind is kind of within the bound of the clock skew. So stragglers are self-healing. So for example, here, if process 1 sends an event to process 0 or like either it can be part of a clock synchronization protocol, or it can be a message sent, or it can be a transaction command, it can be literally anything, it's just one event. And it will bring P0's HLC up to date. So stragglers are usually not a huge concern when it comes to the stability and availability of the service. But rushers are much bigger problems. Here, let's say HLC, we are aware of HLC 20 because they are available from P2. And I want to take a consistent snapshot across all 3 processes because that's the one of the main selling points and then the key capability afforded by HLC, right? So I want to take a snapshot at HLC 20. So to do that, first of all, I want to making sure P0 and the P1s, their kind of frontier HLCs have passed HLC 20. Because if not, then you never know. Let's say if I just currently take an HLC snapshot and then P0 and the P1 give me what they have at HLC 8 and 7 respectively, then at that moment in time, maybe it is a snapshot, but there's nothing preventing another transaction coming into P0 and the P1 minted at HLC 9 and 8 respectively. And then later that will basically invalidate my previous snapshot because it's no longer a valid snapshot at HLC 20 because they're missing those future writes that happened before HLC 20. So in order to be able to take a consistent snapshot at HLC 20, each one of the processes from tier has to be past HLC 20. And then the way to do it is to, if the local, for example, in this case, P0 and the P1, their HLCs are quote unquote lagging behind from P2's perspective, then P2 will just send messages to bump their HLCs ahead into 21 for both of them. Then once it does that, then it can take a consistent snapshot across all three, and that will work. But as you can also see that now the rushers are infectious in the sense that now everybody's HLCs are way ahead of physical time or pushing the boundaries of the clock skews, as you can. So here, this is kind of like a major reliability concern because having HLCs rushes ahead, it makes replicas or different shards look like stale because you either have to keep rushing ahead, pumping their HLCs, or you block, you wait. Or if you have replicas, in this case, let's say P1 has its own replica P1 prime, then a read at HLC 20 will always have to fall back to the primary because all the replicas are not even at HLC 8 yet. So that is a major reliability concern and availability concern because you cannot use your replicas to kind of load shed your primary read traffics because everything has to fall back to the primary to have the knowledge that saying like, it is actually the latest. It's just that I don't have the HLC up to date yet. I don't have an HLC as high as 20 yet. So having reliable, so here it comes to a comparison, right? So if the NTP is used to back HLCs, then you have a much bigger uncertainty window, and if there's any guarantee about the uncertainty window at all, but then you are the service is more likely to subject to this type of operational risks. But if the HLC is backed by PTP, which has a much tighter bound and a guarantee on the clock drift and skew, then it becomes much easier for the HLC minting library to reject rushers, so that we can kind of making sure that this never happens, or if it happens, the HLC rushers are only going to rush ahead, a marginal amount of the ahead of physical time, so that dramatically reduces the risk, operational risk of the system. Right. So next we're going to spend most of the rest of the time talking about actual FB clock versus HLCs, now getting most of the things out of the way. So unless specified otherwise, by FB clock, I meant PTP-based FB clock with commit wait. So now we're actually comparing essentially TrueTime / FB clock versus HLC, and then to see their pros and cons. And then remember earlier I said that HLC-based options, that their consistent snapshot has asterisks. Now here we're going to talk about it. So HLC-based snapshots is essentially based on this notion of capturing all that happens before. If the event 1 happens before event 2, then the event 2's HLC must be greater. Hence, if I just take a distributed snapshot at a particular HLC, then it cannot violate this happened before relationship because they're by definition concurrent. So it must be a valid distributed snapshot. That is true, except that there's a line in the paper that's very subtle. It says that the causality relationship captured. called happens before, which means that if it's not captured, it's out of the scope of happen before relationship. So in event E is only happen before event F. If we capture this causality, if they happen in somewhere, let's say outside of the system, that there is also a causality relationship. For example, Alice called Bob on her phone, and then there's a causality between due to this communication. It's not captured in the system. So in the scope of HLC, this is simply considered out of scope. And then it's not captured. This is not happened before relationship. And then they're still just going to close their eyes and claim that it's still a consistent snapshot. So so users can, in this case, users can observe actually anomalies when the system misses out of band communication. Or even if it's in band, it's just like you never capture those, then hence it's not happened. There's no happen before relationship between these two events. So that's why I call HLC-based snapshots internally consistent snapshots. They're still very useful, but there are limitations that we want to call this out. So it basically the snapshot is only consistent internally with respect to the causality that's explicitly captured by doing this HLC propagation and bumping. So anything outside of that scope is essentially you can observe potentially anomalies. So in the diagram here is the graph here is just saying that if there are events outside of this gray circle, then they have there is some out of band communications that's HLC based. The snapshot is not gonna respect this causality. But when it comes to fbclock based snapshots, it is what I call externally consistent. This snapshot is externally consistent because even though you can have communications that's out of band, but all the timestamps are still minted within the system that the property we talked about earlier when it comes to linearizability and then the transaction timestamp ordering properties, they make no assumptions about the happen before relationship. They don't have the fine print that we talked about earlier from HLC, saying like the causality relationship captured is called happen before, right? There's no those fine prints. It just works. And then by doing the commit wait. So all those snapshot afforded by fbclock is going to be externally consistent. And there's another point I would like to make is that so by calling into fbclock and whatnot, it requires you to have some hardware support, but this is not required for example, in a public cloud setting or whatnot. Let's say on my phone, obviously doesn't have atomic clocks, but it can still benefit and still enjoy the externally consistent snapshot because it is very it's easy to just have a client proxy within the scope that has access to atomic clocks to mint the timestamp, and all those consistency properties still holds. So this is basically having PTP and fbclock based snapshots that not only is externally consistent, and then the consistency of it is not limited by the physical footprint of the atomic clocks. So it's very powerful. So here's another comparison between fbclock and HLC is linearizable reads at scale. So in the Spanner paper, I talk about if you're doing a single shard linearizable read, they just send it to the local primary. So that works. And then if you have a lot of traffic, obviously you want to leverage the replicas as well if they can also serve the linearizable reads. And then too much traffic to the primary database is a major reliability risk. You never want to overload your primary because no matter if you do leader election or whatnot, there's always some overhead. And also if you have leader elections, unless you have extra capacity, that's actually a express way towards cascading failures. If like you overload one primary, you can elect another one, and then now you just have fewer replicas, then you can quickly overload the next primary, and then soon you realize that you overload the entire system. So we want to be able to it's very appealing to be able to serve linearizable reads from replicas. And then, so we realized that, similar to what the Spanner paper called out, is that you don't actually need to serve linearizable reads from the primary. You just need to making sure that a reply that's later than when client dispatches the read query. That will be enough to satisfy linearizability in this case for the read. And then so the key challenge in this case is to have the server and the client agree on the minimum safe timestamp for when the read to happen to satisfy linearizability. So how we achieve this in TrueTime is how Spanner does this is that the client will pick a timestamp. That's definitely in the future. So if the read is satisfied at this timestamp on the server, then obviously it's going to be later than when the client dispatches the request, and hence it's satisfied linearizability. And of course, by picking a timestamp in the future, you always run into this possibility of blocking the read because the server doesn't have it. So what do you do now, right? So the paper talks about this as well, and that's why they think for a single shard you can always just fall back to just primary read so that you have less of blocking. But an alternative is actually to also just to push this blocking and sleeping to the client as well. So that usually helps operationally. That helps improve the reliability of a multi-tenant service. So, for example, the client, when it wants to do a linearizable read, and then, for example, the current timestamp is 4, and then want to pick something in the future, absolutely in the future, and I say pick 5. And then the server is only caught up to 3. And then, so instead of sending the request to the server and then holding the connection and waiting and blocking and all that until the server caught up to 5 or timeout and then getting the reply, the client can pick the timestamp first, let's say pick 5, and then just wait on the client. And then do a little bit of waiting, and then send the 5 to the local replica, which has a much higher probability of the local replica has already caught up to timestamp 5, then can serve it out of the local flash or disk. Then that will be much more efficient. And then you do push the cost to a client, but in this case, because the client is the one who wants to have this property, and then they're usually more okay of doing this extra bit of waiting. And then that helps kind of protect the larger shared infrastructure from not to say bad actors, but some pathological workloads that tend to overload and block the service. So in this case, the fbclock affords linearizability at scale, but this is something that HLC is very hard for HLC to do. Without explicit synchronization or coordination, then HLC can achieve sequential consistency, which is also something pretty useful, but weaker than linearizability. Next, let's talk about transaction models afforded by fbclock versus HLC. So if every distributed rewrite transaction is committed at a single HLC, which can be done, and then also assume that every single read-only transaction sees a consistent snapshot at certain HLCs, then the system is serializable by definition. I mean, if we have some tiebreakers between events happening exactly at the same HLCs, then it's a serializable, which is very strong. I mean, if you look at a lot of the databases, I mean, serializability is for a single shard database is usually the strongest isolation level. And the fbclock affords something even better because serializability doesn't say anything about the eventual ordering of all your transactions and its relationship with the physical time. It just says like it's as if all those transactions happens in a certain sequential order. And then that's like the definition of serializability. But by upgrading from HLC to fbclock, we also upgrade serializability to strict serializability, which is essentially saying that not only all those read and write transactions, they happen as if in a sequential order, but that order is also consistent with physical time or any external observers. So that is also, again, very strong. And that is something HLC is very hard for HLC to do. All right, this is the last slide, and then I want to talk about the efficiencies and the scalabilities afforded by fbclock and HLCs. So one way to look at PTP-based fbclock is that it affords coalescing ordering constructions on the host level. So instead of reasoning about happen before relationships for every process based on every message sent or received, which is the HLC approach, so PTP affords a continuous stream of clock synchronization events from which fbclock presents an API that multiple applications on the host can construct orderings without communication. So that is about efficiency. And also remember the previous example about ordering write transactions. So it is way more efficient to construct orderings using fbclock in the window of uncertainties instead of resorting to explicit coordination, which, for example, that practically doesn't work when we're talking about millions of shards. Well, that's it. Thanks. Do you have any questions?
Do you have a link to the paper? Your paper.
Yeah, Lou, do you have a link to the paper you can share?
Yes, I can send it in the chat. Yeah.
Yeah.
Thank you.
Any more questions? See, someone put, oh, you put it in the chat. So maybe Lou, what parts of this are open source and available to the public?
Yeah, that's a good question. TrueTime itself is not, right? This is that's why I think fbclock and the time card is the best open source solution for anyone who wants to leverage this piece of technology and to get all the benefits I talked about. I think Cockroach famously uses HLC, and then they famously try to be the open source version of Spanner. But if you look at their wikis, that they don't rely on atomic clocks. They actually have a couple of famous blog posts talking about well, how do we do it without atomic clocks? But if you read their posts, and then they don't actually offer linearizabilities unless you're willing to make assumptions about the max clock speed, which is not accurate depending on how comfortable you are with the NTP and the clock infrastructure. And then they do have ways for you to passing tokens to capture some type of causalities, which again resorted to explicit coordination and the communication, which again captures causality but doesn't give you linearizability unless you can make assumptions about the uncertainty bound. So this having the open source option for the TrueTime is definitely a big and the PTP, and then having those, then you can get the benefit of really scalable linearizable read and snapshots and externally consistent snapshots and upgrading the transactional and the consistency model of the entire system. So yeah.
So let's say the existing. Go ahead, Lasse. Go ahead.
Okay. I think about this problem a lot. Okay. Have you thought about this? I think about this. So instead of thinking about the earliest possible time that it might be, or the latest possible time it might be, as is currently the case, have you thought about considering it more as a description of a distribution? Okay. So you think more about it in terms of, you could still have those values if you wanted to, but they would be bound they would be essentially values in a particular confidence interval, okay? I think this would be helpful, okay? And then I think what you guys should do, and I have pitched this relentlessly to you, is you should let, you have this problem, okay? If you increase the sampling size, okay, then you get a more narrow distribution, okay? And there's error associated with it because if you have 1 million servers in a data center and 4 different clocks, okay, if you want to increase the transaction rate, okay, this puts the clock under stress, which is why I think the smart thing to do is let different ordinary clocks talk to each other. And in PTP squared, this is what we have. So we have an overlay network where clocks, where clients not only talk to clocks, but they also talk to other clients, because then you can get an increase in the sampling rate. And when you increase the samples, okay, the spread of your distribution narrows, okay, and this means that your confidence interval, because this whole thing about the absoluteness of this is the earliest time and this is the latest time, that's crazy. That doesn't exist. It's a Gaussian distribution. So I think the best way to optimize this problem, okay, is to increase sampling, and the only way you can do that at hyperscale is to let ordinary clocks talk to each other. So this would be my advice.
Yeah, it makes sense in terms of like all these are just probabilities. I think the Google also talked about like the reason why they feel comfortable of depending on this is because they said the probability of having a bad clock is 6 times less likely than a bad CPU, and then so they feel like this is no worse than the assumptions everyone is already making anyway. So, but yeah, definitely, I think
This is good, but a cheap win is a cheap win, right? I mean, that can be. It can be that the sigma is, you know. So it could be that you're right, but even so, I just think it's too cheap a win. I think that I think that the future essentially has sort of meshes for clock distributions, okay? And I think my own personal opinion is that it's nuts when you see NIST having a clock ensemble to synchronize time based on looking at 16 different clocks. And you have GNSS receivers that are looking at time from 24 satellites at a time. Okay, but then you come to the data center, and there, all of a sudden, you believe in determinism that looking at one clock, okay, is good. When actually these days, getting ordinary clocks on different, you know, it becomes much easier to isolate the outliers. This is the smart way to do it, if you ask me. Let's say some people that buy the time beat product buys that one, and in the real world, it works out quite well. Anyway, so yeah, I'm very opinionated about this. Sorry for that, but yeah, I think that's cool.
that makes sense. Thank you.
So the paper you put in the chat is one from Google in 2012.
Yeah, I saw your comment. Like, I think Ahmad probably can have better links to you for the FB clock part if and then time card resources.
Yeah, we have one, Hasham. There is one presentation, I think, from 2 years ago from Kumar and from Yuliang Li. They have everything, and then I think if you go down in the wiki, they should be that from Spanner if you're looking for that paper.
For the FB clock.
Oh no, FB clock, we don't have a paper yet, so we're working on it.
Working on it. Okay, good.
Yeah. But I mean, so far you have access to the Git.
Yeah.
Do you want to put the link for the GitHub for the FB clock? Maybe, yeah. So that one is available, and we're working on a paper to basically describe everything in detail, similar to what was basically with the TrueTime. So it basically, yeah, it will. We're still working on it. So we're gonna still decide which conference we're gonna put it in. So
excellent. Thank you very
but
much.
we're very open. We're very open. We have everything already out. We do things differently. Like we're very open on every step we're taking before even like we're getting like, you know, a paper about it or something. That's how we operate. So
very good.
And another thing, like Lou, like let's say all these databases that we have available, like open source out there, like how can we combine these things with them, or is there something like what's the closest, like let's say with respect to, let's say, CockroachDB, or like I don't know, even things like Ceph, for example. How can we have these things integrated in existing open source packages for distributed databases where you can combine, let's say, different machines and create a quorum?
Yeah, that's a great question. Like, so paths for kind of adoption, like starting with open source databases that already use HLC, like Cockroach and um, is a I think a good step forward because it on the wire it's interoperable. So if we you would assume that like a cockroach will have a single kind of um, place where they mint their hierarchical clocks, and then it becomes tangible to swap it or having the option to replace it with PTP and then calling into a slightly different API. The integration surface appears to be small. I think that those are maybe ways to do it, and also um, and then and you know this better than I do, but like there are a lot of public clouds that today they also offer some of the better clock synchronization services, but I don't think they this is kind of slightly beyond the slightly beyond distributed databases, but I think different cloud vendors they also provide clock synchronization services, and that might be interesting in Go as well.
And then let's say, for example, Ceph. Is there any way, let's say, that can be added to Ceph, or like, is there already a fork, or like if you want to add HLC, let's say, to a database?
Yeah.
That's probably a question for Pasi, because that's a Red Hat thing. Pasi, anything you can add about Ceph?
Not at the moment. I haven't been digging on that use case recently. We certainly have people who could take it on. The problem is that we don't universally have like a very accurate time on our customer deployment, so that slows things down a little. It's not like we can't do it, but the reality of what people are actually running right now.
And then maybe this question that I will regret if I didn't ask: if you have PTM on the machine, how would things turn, Lou?
Oh, so can you see the question again?
If you have PTM enabled, would that make things better, or you're stuck also with a cal theory that you cannot benefit more if you go lower than the latency? I think you're stuck with cal here as well.
That is, yeah, I need to think more about it, but like, naively, I think so. But
I mean, if it comes for free, great, right? Because then you have a better like window of uncertainty. Your tail is like chopped, pretty much, because you have hardware. There is no software involved anymore. But would you really gain anything? Like, again, that's something. Maybe again in the paper we can think about it all, like put it somehow in the back of it, like a comparison when we have PTM or not, because we have it anyways, so we can test that.
yeah.
Okay, any more questions from the audience? Hearing none, let's give everyone back 8 minutes. Great. See you guys in 2 weeks. Bye, everyone.